Hello everyone. In this video, I am going to discuss Otto cycle, which was invented by Dr. N. A. Otto in 1876. This cycle consists of four processes: two adiabatic process and two constant volume process. As we all know, in Otto cycle we have four stroke: first suction stroke, then compression stroke, then expansion stroke, and last is exhaust stroke. In this diagram, first of all we will plot PV diagram in which pressure is marked on y-axis and volume is marked on x-axis. Here the 0 to 1 line shows the suction stroke in which volume is increases and it is at constant pressure. Our next stroke start with point 1 and its end at point 2, which is isentropic compression, or we can also call it as adiabatic compression, which is denoted by PV to the power gamma equal to constant, which we have already discussed in thermodynamic processes. Then heat is added at constant volume by the help of spark ignition. Next process is isentropic expansion or adiabatic expansion, which is shown by a curve 3 4. Then heat is also rejected at constant volume, and the last stroke is completed with the line 1 0, which is known as exhaust stroke. Now, as we have shown the diagram, the all various processes on PV diagram, here we can see that volume at point 2 is equal to volume at point 3. So we can write V3 equal to V2 and V4 equal to V1. Now we will calculate the thermal efficiency of an Otto cycle, and the basic formula for thermal efficiency is work done upon heat supplied. As we all know, the work done we have written is heat supplied minus heat rejected. So Qs minus Qr upon Qs. So our formula became 1 minus Qr upon Qs. As in this diagram, heat is added at constant volume and heat is also rejected at constant volume. और हम सभी ने थर्मोडायनेमिक प्रोसेस में पढ़ा था कि कांस्टेंट वॉल्यूम पर जो हीट का सप्लाई होती है उसका फॉर्मूला होता है mCv delta T, that is change in temperature. So we can write the formula mCv T3 minus T2 for heat supplied, and for heat rejected mCv T4 minus T1. Now we will put these value in thermal efficiency formula. We will get 1 minus mCv T4 minus T1 upon mCv T3 minus T2. mCv will cancel out, then we will get 1 minus T4 minus T1 upon T3 minus T2. Now we will calculate the value of T3 and T2 in term of T4 and T1 with the help of process 1 to 2 and process 3 to 4. First of all, I will explain the compression ratio, which is denoted by R. Compression ratio is the ratio of total cylinder volume when the piston is at bottom dead center, which is shown by V1. As we can see in the figure PV diagram, that this is the maximum volume which the cylinder contains, that is V1, and this volume is the V2, that is clearance volume. So it is a ratio of total cylinder volume upon clearance volume. So we will write for process 1 to 2, we can write P1 V1 to the power gamma equal to P2 V2 to the power gamma. Then we will calculate here P1 upon P2. P2 is shifted here and V1 is shifted here, so it becomes V2 upon V1 to the power gamma. Now our formula become P1 upon P2 equal to 1 upon R. Why 1 upon R? Because we have replaced V1 upon V2 with compression ratio. So it becomes 1 upon R to the power gamma. As we have already discussed the general formula, that is PV equal to mRT, and here R is characteristic gas constant. So with that formula we get P1 V1 upon T1 equal to P2 V2 upon T2. So if we will put the value of P1 upon P2 in this formula and V1 upon V2 equal to R in this formula, then we will get 1 upon R to the power gamma in place of P1 upon P2 and V1 upon V2 as R equal to T1 upon T2. So from here we get T2 equal to T2, we have shifted here and we get T2 equal to T1 into R to the power gamma minus 1, because R to the power gamma is shifted here and R goes to the denominator, so it become R to the power gamma minus 1. Then we will solve for process 3-4 in the same way, and if we will solve, then we will get T3 equal to T4 into R to the power gamma minus 1. As we have already discussed, the process 3 to 4 is adiabatic expansion process. So we know the adiabatic expansion, we can write PV to the power gamma equal to constant, because it is for process 3 to 4. So we will write P3 V3 to the power gamma equal to P4 V4 to the power gamma, and the compression ratio will be the same as V1 upon V2, and we can write V1 equal to V4 and V2 equal to V3. Now we will put the value of T2 and T3 in thermal efficiency formula. Here it is given 1 minus T4 minus T1 upon T4. Why T4 R to the power gamma minus 1? Because I have replaced T3 with this value and I have replaced T2 with this value, so it becomes T1 R to the power gamma minus 1. Now we can take R to the power gamma minus 1 common from these two values. So we will get T4 upon T4 minus T1 in denominator, which will be cancelled out. Then the formula become thermal efficiency of Otto cycle is 1 minus 1 upon R to the power gamma minus 1. As with the help of formula, we can conclude that Otto cycle depends only on compression ratio R, and here gamma is adiabatic index and the value of gamma is equal to 1.4 only for air. That's all I want to explain in this video. Thank you.